7 miles down. That is where the deepest place on Earth sits. We have mapped distant galaxies and sent robots to Mars. Yet this chasm in our own ocean remains mostly untouched. Something down there resists us. Tonight, you will learn why the Mariana Trench may never truly be explored. If you love the mysteries of the deep, subscribe now. Let's descend. The Mariana Trench lies in the western Pacific Ocean, east of the Philippines and south of Japan. It stretches for over 1,500 miles in a crescent shape. Imagine a scar on the ocean floor. That gives you the picture. The trench sits where two massive pieces of Earth's crust meet. One slides beneath the other, tearing open the deepest wound our planet has. Most people know Mount Everest towers at 29,000 feet. The Mariana Trench goes deeper than that mountain is tall. If you placed Everest at the bottom, its peak would still sit more than a mile underwater. That comparison sounds simple. It hides the terror. Mountains reach into open air where humans can breathe and see. The trench plunges into absolute blackness where pressure turns steel into crumpled foil. 7 miles down means something specific. Every 33 feet of depth adds another atmosphere of pressure. At the trench's deepest point, you face over 1,000 atmospheres pressing on every square inch. A human body would collapse instantly. Even submarines designed for deep water cannot reach the bottom without risking catastrophic implosion. The trench is not just deep. It is hostile in ways that defy our technology. Few places on Earth remain unexplored. We have satellites watching every inch of land. Drones fly over jungles and deserts. Yet 95% of the ocean remains unseen by human eyes. The Mariana Trench represents the final frontier. It holds secrets about how life began, how our planet formed, and what creatures evolved in total isolation. Scientists believe organisms down there have adapted to conditions that would kill anything from the upper ocean in seconds. The trench formed over 50 million years ago. Tectonic forces continue shaping it today. The Pacific Plate grinds beneath the Mariana Plate at a rate of 2 to 3 inches per year. That slow collision creates the deepest depression on Earth. Geologists study the trench to understand earthquakes and volcanic activity. What happens 7 miles down can trigger tsunamis that devastate coastlines thousands of miles away. Temperature at the bottom hovers just above freezing, 36 degrees Fahrenheit, cold enough to slow chemical reactions, yet life persists. Single-celled organisms thrive in mud that has not seen sunlight in millennia. Fish with translucent skin glide through currents strong enough to topple buildings. The ecosystem down there operates on rules we are only beginning to understand. Exploring the Mariana Trench means confronting our limitations. We built rockets that escaped Earth's gravity. We split atoms and mapped the human genome. Yet a column of seawater defeats us. The trench reminds us that depth, darkness, and pressure create barriers our current technology cannot overcome. Every attempt to explore it pushes engineering to the breaking point, and sometimes beyond. The Challenger Deep sits at the southern end of the Mariana Trench. It holds the record as the deepest known point on Earth. The exact depth varies depending on who measured it and when. Most estimates place it between 35,800 and 36,000 feet below sea level. That is nearly 7 miles straight down. The name comes from the HMS Challenger, a British survey ship that first measured the trench's depth in 1875. Using weighted lines, the crew recorded a depth of over 26,000 feet. They were off by nearly 10,000 feet. Early measurements lacked precision, but they proved something profound existed down there. Something deeper than anyone imagined. Later expeditions refined the numbers. In 1951, another HMS Challenger, this one equipped with echo-sounding equipment, measured depths exceeding 35,000 feet. The term Challenger Deep stuck. It became shorthand for the abyss, the place where Earth's ocean reaches its maximum depth, where pressure peaks, where light never arrives. Reaching the Challenger Deep requires more than a submarine. It demands a specially designed vessel capable of withstanding over 8 tons of pressure per square inch. Standard military submarines crush at depths below 2,000 feet. Research submersibles typically max out around 20,000 feet. The Challenger Deep exists in a realm beyond conventional engineering. Only a handful of vehicles ever built can survive the journey. The first confirmed human visit to the Challenger Deep happened in 1960. Before that, it remained a number on a chart, a theoretical point marked by sonar pings bouncing off the seafloor. Scientists debated whether life could exist at such depths. Some believed the pressure would sterilize the environment completely. Others suspected microbes might cling to existence. Nobody knew for certain. The only way to find out was to go there. Measuring depth in the Challenger Deep proves harder than you might think. The ocean floor is not flat. It consists of ridges, valleys, and slopes. Sound waves take time to travel down and back. Temperature and salinity affect how fast sound moves through water. Modern multi-beam sonar systems map the bottom with incredible detail. They reveal a landscape as complex as any mountain range on land. Some areas of the Challenger Deep remain unmapped. New measurements occasionally discover slightly deeper pockets. The search for the absolute deepest point continues. The Challenger Deep represents more than a geographic curiosity. It symbolizes the unknown. Every time humans reach it, they find something unexpected. Strange creatures, unusual rock formations, evidence of processes that do not occur anywhere else on Earth. Each visit raises more questions than it answers. The Challenger Deep holds mysteries that may take centuries to unravel, if we ever manage to explore it thoroughly. Standing on the shore of the Pacific Ocean, you cannot fathom what lies beneath. Waves crash, seagulls cry, children build sandcastles. 7 miles down, in perpetual darkness and crushing pressure, the Challenger Deep waits, silent, cold, indifferent to our curiosity. On January 23rd, 1960, 2 men climbed into a steel ball and descended into the unknown. Jacques Piccard, a Swiss engineer, and Don Walsh, a United States Navy lieutenant, piloted the bathyscaphe Trieste to the bottom of the Challenger Deep. Their journey took 4 hours and 48 minutes. They became the first humans to reach the deepest point on Earth. The Trieste looked like no other vessel. Picture a massive float filled with gasoline attached to a small pressurized sphere. The float provided buoyancy. The sphere housed the crew. The entire contraption weighed over 50 tons when loaded with iron ballast. The design was simple and terrifying. If anything went wrong at depth, the men inside would die instantly. No rescue was possible. No escape existed. Piccard's father, Auguste Piccard, designed the bathyscaphe concept. He understood that conventional submarines could not reach extreme depths. Their hulls, designed for buoyancy and speed, would collapse. The Trieste used a different approach. The crew sphere was made of steel 5 inches thick. It could withstand enormous pressure because it was small and perfectly round. Pressure distributed evenly across its surface. The gasoline float, less dense than water, kept the sphere from sinking uncontrollably. Descending took hours. Piccard and Walsh sat in near total darkness, watching instruments and listening for any sign of structural failure. At around 30,000 feet, they heard a loud crack. Something had broken. They faced a choice: abort and surface, or continue and risk catastrophe. They decided to keep going. The crack, they later discovered, came from a small exterior window. It held, barely. At 35,800 feet, the Trieste touched bottom. Piccard and Walsh became the first people to see the deepest part of the ocean with their own eyes. They stayed for 20 minutes. Their view through the tiny porthole revealed a barren landscape. Silty mud stretched in all directions. Then, something moved. Picard spotted a flatfish, about a foot long, lying on the seafloor. That single sighting shattered the theory that life could not exist at such depths. If a fish could survive down there, what else might be lurking? The ascent took 3 hours and 17 minutes. The Trieste dropped its iron ballast and rose slowly toward the light. When the sphere breached the surface, Navy ships rushed to retrieve it. Picard and Walsh emerged, shaken and triumphant. They had proven human exploration of the deepest ocean was possible. They had also proven it was incredibly dangerous. The Trieste never returned to the Challenger Deep. The Navy used it for other deep-sea missions, then retired it. The bathyscaphe now sits in a museum. Picard and Walsh became legends. Their dive remains one of the most audacious feats in exploration history. 2 men, a steel ball, and sheer determination. That is all it took to conquer the abyss. Or so it seemed. For over 50 years, no one repeated the journey. The Trieste proved the Challenger Deep was reachable. It also proved the cost and risk were enormous. Building a vehicle capable of surviving the descent required resources most governments and institutions were unwilling to commit. Space exploration captured public imagination and funding. The deep ocean faded from priority. Picard and Walsh's record stood unchallenged for 5 decades. Their dive taught us one crucial lesson. The Mariana Trench does not want visitors. Every bolt, every seal, every piece of equipment must be perfect. One flaw means death. The pressure at the bottom allows no margin for error. Engineers learned from the Trieste's design, but replicating it proved harder than expected. The materials, the precision, the testing required push budgets into tens of millions of dollars. For years, no one thought it worth the expense. 36,000 feet below the ocean's surface, pressure reaches levels that defy human intuition. Imagine an elephant standing on your thumbnail. Now imagine 1,600 elephants standing there. That approximates the force pressing on every square inch at the bottom of the Mariana Trench. Over 8 tons per square inch, or 16,000 pounds, more pressure than anywhere else on Earth. Human bodies are mostly water. Water does not compress easily. That fact leads some people to believe pressure might not affect us much. They are wrong. The air spaces in our bodies, lungs, sinuses, ears, would collapse instantly. Ribs would shatter. Organs would rupture. A human without protection would be crushed into a mass barely recognizable as a person. Death would come faster than thought. Materials behave strangely under extreme pressure. Steel, one of the strongest substances we know, can crumple like paper. Engineers discovered this the hard way during early submersible tests. Unmanned probes sent to the trench sometimes returned, mangled beyond recognition. Pressure found weaknesses in welds, seals, and joints. It exploited them ruthlessly. A tiny air bubble trapped in metal during manufacturing can become a catastrophic failure point at depth. Pressure does more than crush. It changes how things work. Electronics malfunction. Batteries drain faster. Chemical reactions slow or stop. Oil thickens. Lubricants fail. Everything designed for surface conditions must be rethought for the deep. Even simple mechanisms like hinges and valves require special engineering. The environment at the bottom of the trench is as alien as the surface of another planet. More so, in some ways. At least Mars does not try to squeeze you out of existence. The Trieste's cruisphere had to be nearly perfect. A sphere distributes pressure evenly, the strongest shape for resisting compression. But the porthole, a flat piece of acrylic, remained a weak point. Engineers made it cone-shaped, wider on the outside than the inside. Pressure pushed it deeper into its housing, creating a tighter seal as depth increased. Brilliant design. Yet during Picard and Walsh's dive, that window cracked. They heard it. They felt it. The fact that it held remains a minor miracle. Glass implodes under pressure at depth. The implosion happens faster than sound. A glass sphere the size of a basketball would shatter into dust before you could blink. The energy released would rival a small bomb. Submersibles operating near the seafloor sometimes encounter these implosions when glass floats or instruments fail. The sound echoes for miles underwater, a reminder of what happens when pressure wins. Modern materials help. Titanium alloys resist pressure better than steel. Ceramic composites offer strength without weight. Carbon fiber, carefully layered, can handle compression that would destroy other materials. Yet even with these advances, designing a vessel for the Challenger Deep remains extraordinarily difficult. Every component must be tested to destruction and beyond. Every seal must be redundant. Every system must have backups for the backups. Pressure affects more than just the vessel. It affects mission planning. How long can you stay at depth before systems begin to degrade? How do you manage ballast when tiny changes in weight mean the difference between sinking and rising? How do you communicate with the surface when radio waves do not penetrate water? Every question leads to more questions. Engineers spend years solving problems most people never consider. The human body evolved for sea level. We thrive at 14.7 pounds per square inch. That is normal atmospheric pressure. Climb a mountain and pressure drops. You feel it in your ears. Dive a few feet underwater and pressure increases. You feel it in your sinuses. Now, multiply that by 1,000. The Mariana Trench exists in a pressure regime so extreme it might as well be another dimension. We can build machines to go there. We cannot send ourselves without becoming passengers inside those machines. Completely dependent. Utterly vulnerable. 12 people have walked on the moon. Only 3 have visited the bottom of the Mariana Trench. That fact surprises most people. Space seems farther, more dangerous, more expensive to reach. Yet we have sent astronauts to the moon multiple times. We have built space stations. We have rovers exploring Mars. The deepest part of our own ocean has seen fewer visitors than the lunar surface. Why? The moon is 250,000 miles away. The Mariana Trench is 7 miles down. Distance does not explain the difference. The answer lies in the nature of the challenge. Space is empty. Vacuum creates problems, certainly. Radiation, temperature extremes, lack of oxygen. But engineers know how to solve those problems. Build a pressure vessel that holds air inside. Protect against radiation with shielding. Provide life support. Done. The ocean is not empty. It presses from all sides with a relentless force. That force increases with every foot of depth. At the bottom of the Mariana Trench, you face pressure over 1,000 times greater than at sea level. Space suits protect astronauts in vacuum. They would be useless underwater. The materials and techniques required for space exploration do not translate to the deep ocean. Different physics, different engineering, different risks. Launching into space costs hundreds of millions of dollars, but rockets are reusable now. Spacecraft can be mass-produced. Economies of scale apply. Deep-sea submersibles capable of reaching the Challenger Deep are custom-built, one at a time. Each costs tens of millions of dollars. Each requires years of testing. Each can carry only a handful of people. There is no mass market for vehicles that dive 7 miles. No commercial incentive. No way to recoup costs. NASA has a budget measured in billions. Space exploration captures public imagination. Kids dream of becoming astronauts. Movies celebrate space travel. The moon landing remains one of humanity's proudest achievements. Deep ocean exploration lacks that cultural cachet. It is dark, claustrophobic, and dangerous in ways that do not look heroic on camera. No one dreams of sitting in a cramped sphere for hours, descending into blackness, hoping the hull does not fail. The moon has been mapped extensively. We know its surface features. We understand its geology. We can plan missions with confidence. The Mariana Trench remains largely unmapped. Sonar provides rough outlines, but detailed exploration requires sending vehicles down to look around. Every mission is a step into the unknown. That uncertainty makes planning harder. It makes funding harder. It makes everything harder. Political will matters. The space race between the United States and Soviet Union drove moon missions. National pride and military advantage justified enormous expense. No similar competition exists for ocean depth. Reaching the bottom of the Mariana Trench proves little strategically. It offers no military edge, no political capital. Countries invest in what serves their interests. Deep ocean exploration serves science. Science, unfortunately, does not command the budgets that national security does. Technology for space travel advanced rapidly because governments poured money into it. Private companies now join the effort. Reusable rockets bring costs down. Commercial satellites create revenue. Space tourism looms on the horizon. The ocean floor offers no comparable economic opportunity, no minerals worth the cost of extraction, no tourism market for extreme depth dives, no reason for private industry to invest. We have sent robotic probes to the deepest parts of the ocean. Unmanned vehicles gather data without risking human lives. They are cheaper, safer, and often more capable than crude submersibles. If robots can do the job, why send people? That question haunts deep ocean exploration. The answer involves inspiration, curiosity, and the human need to see things for ourselves. But those reasons do not sway budget committees. The moon will always be farther away than the Mariana Trench. Yet, it will likely remain easier to reach. Distance and difficulty are not the same thing. One day, perhaps, technology will make deep ocean exploration routine. Until then, the deepest part of our planet remains among the least visited places in existence. Light defines life on Earth. Sunlight drives photosynthesis. Plants convert light into energy. Animals eat plants or eat other animals that ate plants. The chain begins with light. Remove light and the chain breaks. Or so we thought. The Mariana Trench proved us wrong. 7 miles down, no light has ever reached. Not a single photon from the sun penetrates that deep. Yet life persists. Darkness in the trench is absolute. Not the darkness of a moonless night. Not the darkness of a cave. Those places still have some light if you wait for your eyes to adjust. The Mariana Trench offers none. Zero light. The kind of darkness that presses against you. The kind that makes you forget what vision means. Humans lose their sense of up and down in such darkness. Time becomes meaningless. Only instruments tell you where you are. Water absorbs light quickly. Red wavelengths disappear first. By 30 feet down, red looks black. Orange and yellow fade next. By 300 feet, only blue light remains. By 1,000 feet, even blue gives up. Below that, the ocean is lit only by bioluminescence, creatures that make their own light. Their glow provides the only illumination in the deep, except at the very bottom. Even bioluminescent creatures are rare in the Challenger Deep. The darkness there is primal. Sunlight provides more than visibility. It provides heat. The ocean's surface warms in daylight. Currents distribute that heat. But currents weaken with depth. The bottom of the Mariana Trench stays just above freezing year-round. Cold and dark. A combination that makes survival almost impossible. Almost. Life finds a way. It always does. The question is how? Without light, plants cannot grow. Without plants, what do animals eat? The answer lies in what falls from above. Dead organisms, waste, bits of organic matter drift down from the sunlit zones. Scientists call it marine snow. It falls slowly, taking weeks or months to reach the deepest parts of the ocean. By the time it arrives, most of its nutritional value is gone, yet creatures at the bottom have adapted to survive on scraps. They have slow metabolisms, they move rarely, they wait. Some organisms in the trench rely on chemosynthesis instead of photosynthesis. They harvest energy from chemicals rather than light. Volcanic vents release sulfur compounds and methane. Bacteria convert those chemicals into usable energy. Other creatures eat the bacteria. A food chain exists independent of sunlight. It operates in the dark. fueled by Earth's internal heat. This discovery changed biology. It suggested life might exist in places previously thought barren. Ice-covered moons, deep underground, anywhere chemistry provides energy. Humans cannot see in total darkness. Our eyes evolved for light. In the trench, submersibles carry powerful lamps. Those lamps reveal a world that has never known brightness. The creatures there have no pigment. No need for color when nothing can see it. Some have eyes, some do not. Some have light-producing organs. They use bioluminescence to hunt or communicate. The darkness is their element. Light is the intrusion. Early explorers wondered if pressure might create some form of light. Perhaps compression generates heat or sparks. It does not. The darkness remains perfect. Only human technology brings light to the abyss. And when that technology fails, as it sometimes does, the darkness reclaims everything instantly. Complete, final, unforgiving. In March of 2012, filmmaker James Cameron squeezed into a lime green submersible and descended alone to the Challenger Deep. His vehicle, the Deep Sea Challenger, took years to design and build. It was narrower than a coffin. Cameron sat upright, knees bent, for the entire journey. The dive took 2 hours and 36 minutes. He became the third person ever to reach the bottom, and the first to do it solo. Cameron is famous for movies, Titanic, Avatar, The Abyss. His films explore oceans and technology and human ambition. But his passion for deep-sea exploration is genuine. He funded much of the Deep Sea Challenger project himself. Millions of dollars, years of planning, all to spend a few hours on the seafloor. Some called it a publicity stunt. Cameron called it a dream. The Deep Sea Challenger was a marvel of engineering. Built primarily from syntactic foam, a material that resists compression, it could withstand the enormous pressure at depth. The pilot sphere was only 43 inches in diameter. Cameron is over 6 feet tall. He had to curl into a fetal position to fit. The submersible had no seats, no room to move, just instruments, cameras, and a tiny viewport. Comfort was not a priority. Survival was. Descending alone meant no backup. If something went wrong, Cameron would die. No partner to help troubleshoot. No second set of hands. Just him and the machine. He carried that weight as the submersible dropped through blackness. At around 3 miles down, he passed the depth where most submarines implode. The pressure at that point already exceeded anything most humans experience. He had 4 miles left to go. Cameron brought cameras, lots of them. The mission was part exploration, part documentary. He wanted to film the bottom in 3 dimensions. High definition. Something no one had done before. The images would reveal details, invisible in earlier dives. They would show the world what the deepest place on Earth looks like. Or so the plan went. Reality proved more complicated. At 35,756 feet, the Deep Sea Challenger touched down. Cameron looked out the viewport. Mud. Pale sediment stretched in every direction. Barren. Lifeless. He moved the submersible forward, searching for something interesting. Anything. The bottom was flat. Dull. He later described it as like landing on the moon. Desolate. Cameron collected samples, sediment cores, water. He deployed instruments to measure temperature and salinity. He filmed everything. But the bottom of the Challenger Deep offered little drama. No strange creatures appeared. No unusual formations. Just endless mud. After a few hours, a hydraulic fluid leak forced him to surface early. The mission was cut short. He had come all that way for a landscape that looked empty. The Deep Sea Challenger mission taught scientists important lessons. The technology worked. The submersible survived. Cameron proved solo dives were possible, but the lack of visible life at the bottom disappointed many. Pickard and Walsh had seen a flatfish during their dive. Cameron saw nothing. Was the fish a fluke? Had conditions changed in 50 years? Or was the Challenger Deep simply too barren for complex life? Cameron's journey reignited interest in deep ocean exploration. His films and interviews reached millions. People who never cared about the Mariana Trench suddenly wanted to know more. That attention brought funding, new missions, new technology. Cameron's dive was not just about reaching the bottom, it was about reminding the world that mysteries still exist in our own backyard. When James Cameron surfaced from his solo dive in 2012, he brought back more than sediment samples and footage. He brought stories of what he saw and what he did not see. Scientists studied his data carefully. The samples revealed microbial life. Bacteria thrived in the mud, but large organisms seemed absent. Cameron spent hours on the bottom and encountered nothing bigger than a microbe. That absence surprised everyone. Or did it? The Challenger Deep is vast. Cameron explored only a tiny section. Imagine landing in a random spot in a desert. You might see sand and nothing else. That does not mean the desert is lifeless. It means you landed in an empty patch. The same logic applies to the trench. Cameron's submersible had limited mobility. He could not travel far. What he saw represented a pinprick sample of an enormous environment. Cameron did not expect the monotony. Movies and documentaries about the deep ocean show bizarre creatures. Anglerfish with glowing lures, giant squid, alien-like jellyfish. Those animals exist. They live in the deep ocean. But most of them live at mid-depths, between 3,000 and 10,000 feet. Below 20,000 feet, life becomes scarce. Below 30,000 feet, it becomes rare. The Challenger Deep sits at the extreme end of that scale. The landscape itself held clues. Soft sediment covered everything. No rocks, no hard structures. Sediment forms from organic material falling from above. Over millions of years it piles up. The layer at the bottom of the trench is thick, meters deep in places. Anything living there must burrow or float just above the mud. Large animals need hard surfaces to anchor themselves or hunt. Without that, they cannot thrive. Cameron noticed the cold. Thermometers registered temperatures just above freezing. At that temperature, metabolism's slow. Creatures move less, hunt less, reproduce less. Energy is scarce. Every calorie counts. Life at the bottom exists on the edge of survival. The animals there are small, slow, and few. Spotting one requires luck and patience. Cameron had time constraints. The hydraulic leak forced him to surface early. He did not have the luxury of waiting for something to appear. One thing did surprise him. Amphipods swarmed his bait traps. These shrimp-like crustaceans appeared within minutes of the traps being deployed. Hundreds of them. They were translucent, eyeless, and voracious. They stripped bait to bone in hours. Cameron had expected scavengers at depth, but not in such numbers. The amphipods proved the Challenger Deep was not barren. Life was there. You just had to look in the right place. Cameron also reported feeling isolated in a way he had never experienced. He had trained for the dive. He knew it would be dark and cramped. But the reality exceeded expectations. No radio contact with the surface. No windows except a tiny porthole. The submersible creaked and groaned under pressure. Every sound made him wonder if something was failing. The psychological weight of being 7 miles underwater, alone, pressed on him as much as the physical pressure pressed on the hull. The Deep-Sea Challenger's cameras captured high-definition footage. Scientists analyzed every frame. They identified bacterial mats, strange formations in the sediment, evidence of bioturbation, the disturbance of mud by living organisms. Something was moving through the sediment even if Cameron could not see it directly. The evidence was there. Subtle, easy to miss, but real. Cameron did not find the smoking gun discovery everyone hoped for. No new species, no alien ecosystem. But absence of evidence is not evidence of absence. His mission proved the Challenger Deep could be reached safely with modern technology. It proved solo dives were viable. It proved we could bring back samples and footage. Those achievements matter. They paved the way for future missions that may yet find what Cameron missed. At the bottom of the Mariana Trench, life exists in forms so alien they redefine what survival means. No sunlight, crushing pressure, near freezing temperatures. These conditions should be lethal. Yet creatures thrive. They have evolved traits, so specialized, so bizarre, that scientists struggle to classify them. 3 groups dominate the ecosystem at depth: snailfish, amphipods, and xenophyophores. Each represents a different solution to the same problem: how to live where nothing should. Snailfish hold the record for the deepest living fish ever recorded. In 2017, researchers filmed a type of snailfish at 27,000 feet in the Mariana Trench. It looked like a tadpole made of gelatin. Translucent skin, no scales, tiny eyes. It drifted through the water with slow, graceful movements. Scientists estimate snailfish may survive as deep as 28,000 feet. Below that, the pressure exceeds what any fish can tolerate. The chemistry of their cells breaks down. How do snailfish survive pressure that would crush most fish? They lack swim bladders. Swim bladders are gas-filled organs that help fish control buoyancy. At depth, gas compresses. Swim bladders become useless or deadly. Snailfish evolved without them. Their bodies are mostly water and soft tissue. Water does not compress. Soft tissue distributes pressure evenly. They are built to yield rather than resist, like willow trees bending in wind. Amphipods are crustaceans. They look like shrimp, but smaller and stranger. At the bottom of the trench, amphipods grow larger than their shallow water cousins. Some reach lengths of over 12 inches. They are scavengers. When something dies and sinks to the bottom, amphipods find it. They swarm in hundreds, feeding in a frenzy. Researchers use baited cameras to attract them. The footage shows a feeding behavior so aggressive it resembles piranhas. These amphipods have no eyes. Vision is useless in absolute darkness. They navigate by smell and touch. Sensitive antennae detect chemical traces in the water. They can locate a food source from hundreds of feet away. Once they find it, they tear into it with powerful mandibles. Bones, shells, flesh, nothing is wasted. In an environment where food is scarce, amphipods are the cleanup crew. They recycle every calorie. Xenophyophores are the strangest of all. They are single-celled organisms, one cell, yet they grow to sizes visible to the naked eye. Some reach 4 inches across. They live on the seafloor, anchored to sediment. Their bodies are delicate, branching structures that look like alien flowers. Scientists know almost nothing about them. How they reproduce, what they eat, how they grow so large. Xenophyophores represent one of biology's great mysteries. These organisms have been found at the deepest parts of the trench, over 35,000 feet down. They survive pressure that would liquefy most life forms. Their cell walls must be incredibly strong yet flexible. They likely feed on organic particles in the sediment, bacteria, detritus, anything that drifts within reach. They grow slowly. Some may live for decades or longer. Time moves differently at the bottom of the ocean. All 3 groups share common traits: slow metabolisms, long lifespans, minimal energy expenditure. They do not waste movement. They do not waste calories. Every action is calculated. In the deep, efficiency means survival. Waste means death. Evolution has stripped away everything unnecessary. What remains is life reduced to its essence. These creatures also share another trait. They cannot leave. Bring a snailfish to the surface and it dies. The pressure drop causes its cells to rupture. Its body falls apart. The same happens with amphipods and xenophyophores. They are prisoners of depth, adapted so completely to their environment that anywhere else is fatal. The Mariana Trench is not just their home, it is their entire universe. Without sunlight, life on Earth should not exist. Every biology textbook says so. Plants use photosynthesis to turn light into energy. Herbivores eat plants. Carnivores eat herbivores. The food chain starts with the sun. Remove the sun and the chain collapses. That rule holds everywhere on the planet, except at the bottom of the ocean. There, life found another way. Chemosynthesis replaces photosynthesis in the deep. Instead of harvesting energy from light, organisms harvest it from chemicals. Volcanic vents and seeps release compounds like hydrogen sulfide and methane. These chemicals are toxic to most life, but certain bacteria can break them down and extract energy. The process is called chemosynthesis. It is less efficient than photosynthesis. It produces less energy, but in the deep ocean, it is enough. These bacteria form the base of a food chain independent of sunlight. They grow in thick mats on rocks and sediment near vents. The mats look like white or yellow carpets. Other organisms graze on the bacteria. Tube worms, clams, and crabs cluster around vents, feeding on the microbial community. These ecosystems thrive in one of the harshest environments on Earth. They prove life does not need light. It only needs energy. The Mariana Trench has volcanic vents. Magma heats seawater, which seeps through cracks in the seafloor. The superheated water dissolves minerals and chemicals from surrounding rock. When it erupts back into the ocean, it carries those chemicals with it. The water can reach temperatures over 700 degrees Fahrenheit, hot enough to melt lead. Yet bacteria survive at the edges, where temperatures drop to a more tolerable range. Bacterial mats at the bottom of the trench feed more than just microbes. They support entire communities. Small crustaceans scrape bacteria off rocks. Fish eat the crustaceans. Larger predators eat the fish. The chain mirrors surface ecosystems, but operates on a different fuel: chemicals instead of light. The discovery of chemosynthesis changed our understanding of where life can exist. If life thrives at the bottom of the ocean, it might thrive on other planets. Moons with subsurface oceans, ice-covered worlds, anywhere chemistry provides energy. Scientists have found chemosynthetic bacteria in mud samples from the Challenger Deep. These bacteria process organic compounds that drift down from above. They break down molecules and extract whatever energy remains. They are the ultimate recyclers. Nothing goes to waste. Every atom is used. The efficiency rivals anything evolution has produced. Bacterial mats also play another role. They produce oxygen. Not much. A tiny amount compared to surface photosynthesis. But in the deep ocean, every bit of oxygen matters. Some organisms rely on that oxygen to survive. Without bacterial mats, the deep would be even more hostile. The mats create pockets of habitability in an otherwise lifeless wasteland. Chemosynthesis is slower than photosynthesis. Bacteria grow at a fraction of the rate surface algae do. Energy yield is lower, but the process is reliable. Volcanic vents operate for thousands of years. Chemical seeps flow continuously. The energy source is stable. Organisms that depend on chemosynthesis do not face seasonal changes. No winter, no summer, just a steady supply of chemicals. That stability allows life to persist in places where sunlight never reaches. The Mariana Trench proves a fundamental truth. Life adapts. It exploits every possible niche. It finds energy in unexpected places. The deep ocean is dark, cold, and hostile, yet it teems with microscopic life. Bacteria thrive where nothing else can. They build ecosystems from scraps. They survive on chemistry alone. They remind us that life is not fragile. It is relentless. The Mariana Trench did not appear overnight. It formed over tens of millions of years through a process called subduction. Two massive slabs of Earth's crust, tectonic plates, collide at the trench. One plate slides beneath the other. The Pacific plate dives under the smaller Mariana plate. As it descends, it tears open a gash in the seafloor. That gash is the trench, the deepest wound on Earth's surface. Tectonic plates float on the mantle, a layer of semi-molten rock beneath the crust. Convection currents in the mantle push plates around, Some plates move apart, some collide. Where they collide, one usually goes under. The denser plate subducts. The Pacific plate is denser than the Mariana plate. It sinks, slowly, relentlessly, at a rate of about 2 to 3 inches per year. That may sound slow. Over millions of years it adds up. As the Pacific plate descends, it pulls the seafloor down with it. The edge of the plate bends and cracks. Earthquakes ripple through the region. Magma rises from the mantle to fill gaps. Volcanic islands form parallel to the trench. The Mariana Islands sit on the overriding plate. They are the visible part of a much larger volcanic arc. Below them, magma churns and rises, driven by the heat of subduction. The trench itself is shaped like a crescent, over 1,500 miles long, an average of 43 miles wide. The deepest parts lie near the southern end. The northern sections are shallower, though still incredibly deep by any standard. The shape reflects the geometry of the collision. Plates do not meet head-on. They grind at angles. The trench follows the line where the Pacific plate bends downward. Subduction zones are among the most geologically active places on Earth. The pressure and friction of one plate diving under another generate enormous energy. That energy is released as earthquakes, volcanic eruptions, and tsunamis. The Mariana Trench sits within the Ring of Fire, a belt of seismic activity encircling the Pacific Ocean. More than 75% of the world's earthquakes occur in the Ring of Fire. The trench contributes to that number. Deep beneath the trench, the descending Pacific plate heats up. It carries water trapped in minerals and sediments. As temperature and pressure increase, that water is released. It rises into the mantle above, lowering the melting point of rock. Magma forms. The magma is less dense than surrounding rock. It rises toward the surface, feeding volcanoes on the Mariana Islands. The cycle continues. Water descends with the plate. Magma rises. Volcanoes erupt. The process has been ongoing for millions of years. The trench will continue to deepen. As long as the Pacific plate keeps moving, the trench will keep growing. Subduction grinds away at the crust, dragging it down into the mantle. Eventually, miles below the surface, the crust melts and becomes part of the mantle again. The cycle is called the rock cycle. Crust forms at mid-ocean ridges. It spreads across the seafloor. It subducts at trenches. It melts and returns to the mantle. Millions of years later, it erupts as lava and forms new crust. The cycle has no beginning or end. Studying the Mariana Trench helps scientists understand subduction. How fast does it happen? What triggers earthquakes? How much water is carried into the mantle? These questions have implications far beyond the trench. Subduction zones exist around the world. They threaten coastlines with earthquakes and tsunamis. Understanding how they work can save lives. The trench is a window into Earth's interior. Sediment cores pulled from the bottom contain minerals that form deep in the mantle. Rocks from the trench reveal clues about temperatures and pressures miles below the surface. Every sample tells a story. Every measurement adds to our understanding. The Mariana Trench is not just a hole in the ocean. It is a laboratory for studying the planet itself. The Mariana Trench does more than sit quietly at the bottom of the ocean. It generates earthquakes, big ones. The subduction zone beneath the trench is one of the most seismically active regions on Earth. When stress builds up between the Pacific plate and the Mariana plate, it eventually releases. The release comes as an earthquake, sometimes a catastrophic one. Tremors born 7 miles deep can shake the entire Pacific Rim. Subduction zone earthquakes differ from shallow quakes. They occur at greater depths, 10 to 30 miles below the seafloor, sometimes deeper. The energy travels farther. A magnitude 7 earthquake in the Mariana Trench can be felt hundreds of miles away. Seismometers around the Pacific pick up the signal. The Earth rings like a bell. The vibrations travel through rock, water, and air. They do not stop until the energy dissipates. The magnitude of an earthquake depends on how much stress is released. Stress builds as tectonic plates grind against each other. Friction locks them together. Pressure increases. Eventually, the friction fails. The plates slip. The sudden movement releases energy in all directions. The more stress built up, the larger the quake. Subduction zones can store stress for centuries before releasing it in one catastrophic event. The 1952 Mariana Islands earthquake measured magnitude 7.5. It struck near the trench at a depth of over 10 miles. The quake damaged buildings on Guam and triggered landslides. Aftershocks continued for weeks. Scientists studied the event to understand how energy propagates through subduction zones. The data revealed that the Pacific Plate was descending at an angle, creating complex stress patterns. Those patterns make predicting future quakes nearly impossible. Earthquakes in the trench can trigger tsunamis. When the seafloor moves suddenly, it displaces water. That displacement creates waves. In deep water, tsunami waves are small and fast. They travel at hundreds of miles per hour. When they reach shallow coastal waters, they slow down and grow. A wave a few feet tall in the open ocean can become a 30-foot wall of water on shore. The 1952 quake did not generate a major tsunami, but larger quakes in the region have. The potential for a megaquake haunts seismologists. Subduction zones can produce magnitude 9 earthquakes, the largest ever recorded. The 2004 Indian Ocean quake was magnitude 9.1. It killed over 200,000 people. The 2011 Tohoku quake in Japan was magnitude 9.1. It triggered a tsunami that destroyed entire towns. The Mariana Trench subduction zone has not produced a megaquake in recorded history. That does not mean it cannot. Scientists monitor the trench with seismometers and ocean bottom sensors. They measure small quakes continuously. Most are too weak to feel. Magnitude 3 or 4. They represent minor releases of stress, but they also indicate where pressure is building. Clusters of small quakes can precede larger ones. Sometimes, earthquake prediction remains imperfect. We know stress is accumulating. We do not know when it will release. Every earthquake in the Mariana Trench teaches us something. How plates interact, how energy transfers through rock, how often large quakes occur. The data helps build models. Those models improve hazard assessments. Coastal cities around the Pacific use those assessments to prepare building codes, tsunami warning systems, evacuation plans. The trench is far from civilization, but its effects reach everywhere. The Mariana Trench is not just a creator of earthquakes, it is a reminder of the planet's power. Earth's crust is thin, fragile. Beneath it lies unimaginable energy. That energy drives continents, builds mountains, opens oceans, and occasionally it reminds us that we live on a dynamic, ever-changing world, one that does not care about our cities or our plans. Sound behaves strangely underwater. It travels faster than it does in air, about 4 times faster, and it travels farther, much farther. In the deep ocean, sound can cross entire basins. A whale singing off the coast of Australia can be heard near Antarctica. This happens because of something called the sound channel. And at the bottom of the Mariana Trench, that channel becomes a highway for noise. The sound channel, officially called the SOFAR channel, exists at a specific depth where sound waves bend and trap themselves. Temperature and pressure affect how fast sound travels. Cold water slows sound down, high pressure speeds it up. At around 3,000 feet, these effects balance. Sound waves emitted at that depth refract back toward the channel. They bounce between layers of water without reaching the surface or the seafloor. Sound can travel thousands of miles this way. At the bottom of the Mariana Trench, sound behaves differently. The depth is so extreme that pressure dominates. Sound travels faster there than anywhere else in the ocean. Over 5,000 feet per second. An explosion at the bottom would be heard across the Pacific in minutes. The trench acts as a natural amplifier. Noise generated at depth does not dissipate quickly. It echoes, it lingers, it travels. Military submarines use the sound channel to communicate. A low-frequency signal can reach across oceans without needing powerful transmitters. During the Cold War, both the United States and Soviet Union deployed underwater listening stations to monitor submarine activity. They listened for propeller noise, engine vibrations, anything that might reveal an enemy vessel. The sound channel made that possible. It turned the ocean into a giant listening device. Marine mammals also use the sound channel. Whales produce low-frequency calls that travel hundreds of miles. They communicate across vast distances, find mates, warn of danger. The ocean is dark. Sound replaces vision. For creatures living at depth, sound is everything. They navigate by echolocation. They hunt by listening for prey. They avoid predators by detecting movement. The deep ocean is not silent. It hums with life. Human activity adds to the noise. Ship propellers, sonar, offshore drilling, underwater construction. All of it creates sound that propagates through the ocean. Some frequencies interfere with marine life. Whales change their calls to avoid noise pollution. Fish avoid loud areas. The sound channel, that once carried natural signals, now carries industrial noise. The long-term effects remain unknown, but scientists worry. At the bottom of the Mariana Trench, even small sounds matter. The snap of a shrimp's claw, the scrape of sediment moving, the creak of a submersible's hull. Everything is amplified by the environment. Explorers report hearing strange noises at depth. Groans, clicks, thuds. Some are biological, some are geological. The trench is alive with sound. You just need the right equipment to hear it. Sound also helps scientists map the trench. Sonar sends sound waves down and measures how long they take to bounce back. The time delay reveals depth. Modern multi-beam sonar systems create detailed maps of the seafloor. They show ridges, valleys, and slopes invisible to cameras. Sound penetrates the darkness. It reveals the shape of the abyss. Without sonar, we would know almost nothing about the trench's topography. Sound travels so efficiently in the deep that submarines have to be quiet. A noisy submarine can be detected from hundreds of miles away. Engineers design holes to minimize vibration. Propellers are shaped to reduce cavitation, the formation of bubbles that create noise. Every moving part is dampened. Silence is survival. The ocean listens. And in the Mariana Trench, it listens very well. In 2019, explorer Victor Vescovo descended to the bottom of the Challenger Deep. He brought cameras, scientific instruments, and sample collection tools. When he reviewed his footage, he found something no one wanted to see. A plastic bag, resting on the seafloor, 7 miles down, in the most remote place on Earth. Humanity's trash had arrived. Plastic pollution is everywhere. Beaches, rivers, ocean gyres. Microplastics have been found in Arctic ice and Antarctic snow. But finding a plastic bag at the deepest point on Earth shocked scientists. It meant pollution reached places humans had barely visited. The bag likely drifted down over weeks or months. Currents carried it, gravity pulled it. Eventually it settled on the bottom. There it will remain for centuries, maybe longer. Plastic does not decompose in the deep ocean. Vescovo also found candy wrappers and other debris. Not much, but enough to confirm the trench was not pristine. Oceanographers had suspected pollution reached the deepest zones. Vescovo's dive provided proof. Subsequent missions found more. Microplastics in sediment samples, synthetic fibers in amphipod tissue. The creatures at the bottom were ingesting plastic. It was entering the food chain. How does plastic reach the trench? Most ocean pollution comes from land. Rivers carry trash from cities to the coast. Currents distribute it. Some plastic floats, some sinks. Dense plastics like bottles and bags filled with sediment descend. They drift with deep currents until they reach the seafloor. The Mariana Trench sits at the bottom of a vast funnel. Everything that sinks in the Western Pacific eventually ends up there. Microplastics are worse than large debris. They break down from bigger pieces. UV light, wave action, and time shatter plastic into fragments smaller than a grain of rice. These particles are nearly impossible to remove from the ocean. They persist for decades. Animals mistake them for food. The particles clog digestive systems. They leach toxic chemicals. Some of those chemicals disrupt hormones. They cause reproductive failures. The long-term ecological impact remains unknown. Chemical contamination accompanies plastic. PCBs, flame retardants, and pesticides bind to plastic surfaces. Those chemicals hitch rides to the deep ocean. When amphipods ingest microplastics, they absorb the chemicals. Predators that eat amphipods accumulate even higher concentrations. This process, called biomagnification, moves toxins up the food chain. Apex predators carry the highest loads. The deepest parts of the ocean are becoming toxic waste dumps. The discovery of pollution at the bottom of the trench forced a reckoning. We assumed the deep ocean was too remote to damage. We were wrong. Human activity affects every part of the planet. No place is untouched. The Mariana Trench, once a symbol of pristine wilderness, now represents our failure to manage waste. The bag on the seafloor is a monument to carelessness. Cleaning the trench is impossible with current technology. We cannot send enough submersibles to collect debris. We cannot filter microplastics from 7 miles of water. The only solution is to stop pollution at the source, reduce plastic production, improve waste management, prevent trash from reaching rivers and oceans. These actions will not help the plastic already in the trench, but they can prevent more from arriving. Scientists study pollution in the trench to understand its effects. They measure chemical concentrations in sediment. They analyze tissue samples from creatures. They track how pollutants move through the ecosystem. The data is grim. Even the deepest, darkest, most remote environment on Earth is contaminated. If we cannot protect the Mariana Trench, what can we protect? Nuclear submarines can dive deep. Military vessels routinely operate at depths of 1,000 feet. Some specialized submarines reach 2,000 feet. A few experimental models have touched 3,000 feet. Beyond that, pressure becomes insurmountable. Standard submarine hulls crush. The Mariana Trench descends to 36,000 feet. No military submarine can operate there. The technology does not exist. Submarine hulls are designed for buoyancy and speed. They are cylindrical, reinforced with ribs and frames. That design works at moderate depths. It fails catastrophically in the extreme deep. Pressure finds weaknesses, welds crack, seals fail, hatches buckle. At full trench depth, a military submarine would implode in seconds. The crew would have no warning, no time to react, just instant obliteration. Deep-sea submersibles are different. They are not submarines. Submarines are vessels designed to travel long distances underwater. Submersibles are small, specialized craft designed for depth. They sacrifice range and speed for pressure resistance. Most submersibles can reach 10 to 20,000 feet. Only a handful can go deeper. And only 3 vehicles in history have reached the Challenger deep. Each was custom built for that single purpose. The difference lies in design philosophy. Submersibles use thick pressure spheres to protect the crew. The sphere is the strongest shape for resisting compression. It distributes pressure evenly, but spheres are small. They cannot hold much equipment or many people. Submersibles are cramped, slow, and limited in capability. They are research tools, not military assets. Building a submarine that could operate freely at trench depth would require breakthroughs in material science. Current alloys cannot handle the pressure. Titanium is strong but expensive and difficult to work with. Carbon fiber composites show promise but remain unproven at extreme depth. Ceramic materials resist compression but are brittle. Engineers face a paradox. The stronger you make a hull, the heavier it becomes. Heavy vessels require more buoyancy. More buoyancy means larger size. Larger size means more surface area for pressure to act on. Even if materials improved, power remains a problem. Batteries are heavy. They do not provide much energy for their weight. Nuclear reactors work on large submarines but are too big for small submersibles. Fuel cells offer some potential, but operating them at depth introduces new challenges. Every system designed for surface conditions must be rethought. Motors, pumps, electronics, nothing works the same under 8 tons of pressure per square inch. Unmanned vehicles offer a partial solution. Robots do not need life support. They can be smaller and simpler. Remotely operated vehicles, ROVs, have explored the trench multiple times. They collect samples and film the bottom. But they are tethered to surface ships. The tether limits range and creates drag. Autonomous underwater vehicles, AUVs, can operate independently. But at extreme depth, communication becomes impossible. Radio waves do not penetrate water. Acoustic signals are slow and unreliable. The Mariana Trench will likely remain off-limits to submarines for decades, maybe longer. The engineering challenges are too great. The costs too high. The military has no strategic reason to develop such capability. Research institutions lack funding. Private industry sees no profit. Deep-sea exploration depends on a few wealthy individuals and government grants. That is not enough to drive major technological breakthroughs. For now, the trench belongs to a handful of specialized vehicles, built one at a time, operated by experts. Each dive is a major expedition requiring months of planning. The age of casual exploration at full. Ocean depth has not arrived. It may never arrive. Some places on Earth will remain beyond our reach. The Mariana Trench is one of them. So, if the submarines we have now cannot reach the deepest parts of the ocean, what would we actually need to build? The answer is more complicated than just making stronger hulls. Engineers have run the calculations. To explore the Mariana Trench freely, the way we explore shallow seas, we would need materials that barely exist yet. Titanium alloys strong enough to resist 11,000 pounds per square inch. Sapphire viewports thicker than your forearm. Battery systems that can function in near-freezing water under crushing force. Every component would need to be reimagined from scratch. The cost of building just one such vehicle has been estimated at over $200 million. That is for a single submersible. To truly map and study the trench, we would need dozens, perhaps hundreds. The technology gap is not just about money though, it is about physics pushing back. At a certain depth, even the strongest materials we know start to behave strangely. Metal crystallizes differently under extreme pressure. Seals that work perfectly at the testing stage fail catastrophically 7 miles down. Electronics short out for reasons engineers still debate. One proposed solution involves using ceramic hulls instead of metal. Ceramics can handle immense compression without cracking. They have been tested in laboratories at pressures exceeding what exists at the bottom of the trench. The problem is weight. A ceramic sphere strong enough to protect a human crew would weigh over 40 tons. Getting that into the water is one challenge. Getting it back out is another. Some researchers have suggested we stop trying to send humans altogether. Instead, we could deploy swarms of tiny autonomous robots, each one no bigger than a shoebox. They would scatter across the trench floor, recording data, taking samples, streaming video back to ships, on the ocean's top layer. The technology for this exists. Miniature submarines already patrol rivers and lakes. Scaling them up for the deep ocean is theoretically possible. The challenge is power. Batteries drain fast in cold water. Solar panels are useless 7 miles below where sunlight ends. Nuclear power cells could work, in theory. They have been used in deep space probes for decades. Putting them in the ocean raises different questions. What happens if one fails? If it sinks into the sediment and stays there for 1,000 years? These are not easy problems to solve. Another idea involves tethered systems. Imagine a submersible connected to a ship above by a cable thinner than your finger. The cable carries power down and data up. This eliminates the battery problem entirely. The ship provides endless electricity. The submersible never needs to return. It could stay at depth for months, mapping every crevice, filming every creature, collecting samples around the clock. The United States Navy experimented with tethered deep-sea drones in the early 2000s. They worked well at moderate depths. Below 20,000 feet, the cable itself became a problem. Ocean currents pulled it sideways. The drag became so intense that the submersible could barely move. Engineers tried using stronger cables. That made the drag worse. They tried making the cable thinner. It snapped. The perfect cable has not been invented yet. Some scientists believe the real breakthrough will come from biology. There are creatures living at full trench depth right now. Snailfish, amphipods, microbes we have barely studied. Their cells do not collapse under pressure. Their proteins fold in ways that seem impossible. If we could understand how they do it, we might design materials that mimic their chemistry. This field is called biomimicry, learning from life to build better machines. Researchers have already created synthetic gels based on deep-sea organisms. These gels stay flexible under pressures that would shatter steel. They could be used to coat electronics or line the joints of robotic arms. The work is promising. It is also slow. Until we solve these problems, the trench remains mostly beyond reach. We can visit it briefly. We cannot stay. We cannot explore it the way we have explored mountains or deserts or caves. The gap between what we want to do and what we can do has never been wider. The debate over how to explore the trench usually comes down to one question. Do we send robots or do we send people? Both options have fierce supporters. Both have serious flaws. Remotely operated vehicles, or ROVs, have been the workhorses of deep ocean research for decades. They are tough, reliable, and cheap compared to manned submersibles. An ROV can stay underwater for days. It does not need life support. It does not need to come up for air. If something goes wrong, you lose a machine, not a crew. The military uses ROVs to recover wreckage from the ocean. Flaw: oil companies use them to inspect pipelines in the Gulf of Mexico. Scientists use them to film hydrothermal vents and deep-sea coral. They work. The problem is control. Operating an ROV from the deck of a ship 7 miles above is like trying to thread a needle while wearing oven mitts. The signal delay is barely noticeable at shallow depths. At trench depth, it becomes maddening. You push the joystick to move left. 2 seconds pass. Then the ROV moves. By then, you have overcorrected. The camera swings wildly. You lose sight of whatever you were trying to film. This lag has caused researchers to crash expensive ROVs into rock formations more than once. Manned submersibles solve the lag problem. When a human pilot sits inside the vehicle, they see and respond instantly. They can make split-second decisions, navigate tight spaces, react to the unexpected. James Cameron has said that being inside the submersible at trench depth allowed him to notice things a robot would have. Mist. Subtle color changes in the sediment. Tiny movements that hinted at buried life. The human eye, he argued, is still better than any camera. Human intuition is still better than any algorithm. The counter-argument is equally strong. Humans are fragile. They need oxygen, warmth, food, water. A manned submersible must carry all of that, plus backup systems in case the primary ones fail, plus communication equipment, plus thick viewports so the crew can see out. All of this adds weight. Weight requires more powerful thrusters. More powerful thrusters drain batteries faster. Batteries dying at the bottom of the Mariana Trench is not a theoretical problem. It has almost happened. In 1960, the Trieste had just enough power to make it back to the ocean's top layer. Barely. The crew described the ascent as the longest 3 hours of their lives. Victor Vescovo's submersible had better batteries. It also had more redundancy, but even his vehicle could only stay at full depth for a few hours before needing to return. Compare that to an ROV, which can loiter at depth for 16 hours or more. The cost difference is staggering. Building a manned submersible capable of reaching the trench costs upward of $30 million. An ROV with similar capabilities costs 1/10 of that. For the price of one crewed vehicle, you could deploy 10 robots, cover 10 times as much area, collect 10 times as much data. Some scientists argue that sending humans to the deep ocean is a vanity project, a stunt, that the real work can be done cheaper and safer with machines. Others believe the opposite, that robots are tools, useful but limited, that exploration requires presence, requires risk, requires skin in the game. This argument will not be settled anytime soon. For now, we use both. ROVs map large areas quickly. Manned submersibles go where precision and intuition matter most. Neither option is perfect. Both are expensive, both are limited, and both have revealed things that changed what we thought we knew. In 2019, a man named Victor Vescovo climbed into a submersible called the Limiting Factor and descended to the deepest point in all 5 of the world's oceans, one after another. The Atlantic, the Southern Ocean, the Indian, the Pacific, the Arctic. It was the first time anyone had attempted such a journey. The expedition was called the 5 Deeps. It took 2 years. It cost tens of millions of dollars. And what Vescovo found at the bottom of the Mariana Trench shocked even the scientists advising him. At a depth of 35,853 feet, deeper than any human had ever gone, Vescovo looked out through the submersible's viewport and saw something glinting in the sediment. At first, he thought it was a rock. Then the lights caught it differently. It was a plastic bag, wedged into the mud, 7 miles below the ocean's top layer. In the most remote place on Earth, plastic. The discovery made international headlines. It confirmed what researchers had feared, that human pollution has reached even the deepest parts of the planet, that nowhere is untouched. The bag was not the only trash Vescovo found. There were candy wrappers, pieces of metal, fragments of material no one could immediately identify. Later analysis suggested some of it was decades old, dropped from ships long before anyone knew how far debris could travel. Vescovo also found life. Strange, translucent creatures drifting past the viewport. Fish with soft bodies and enormous eyes. Amphipods the size of your hand. One species looked unlike anything catalogued before. Researchers nicknamed it the Mariana Hadal snailfish. It had no scales. Its bones were barely calcified. Its body seemed more liquid than solid. How it survives under that much pressure remains a mystery. The submersible's cameras captured over 200 hours of footage during the 5 Deeps expedition. Most of it has never been made public. What has been released shows a landscape that looks more like an alien moon than Earth. Fields of grey sediment stretching endlessly. Rock formations twisted into shapes that should not exist. Bioluminescent flashes in the darkness. Creatures signaling to each other in ways we do not understand. Vescovo described the experience as deeply humbling. He had expected emptiness. Instead, he found complexity. Not abundant life, like a coral reef, but life that had adapted to the absolute edge of survival. Life that thrived where nothing should. The expedition also tested new technology. The Limiting Factor was designed to dive repeatedly to full ocean depth. Previous submersibles could make 1 trip, maybe 2, before needing extensive maintenance. Vescovo's vehicle completed more than 30 dives below 20,000 feet. It proved that reusable deep ocean exploration is possible. Whether it is practical is another question. The submersible required a support ship, a crew of 30, and months of preparation between dives. The data collected was invaluable. The cost was immense. Still, the Five Deeps expedition accomplished something no one had before. It showed that the deep ocean is not a single environment. Every trench is different. The Mariana is colder than the Tonga Trench. The Java Trench has more seismic activity. The Philippine Trench has different chemistry. Understanding one does not mean understanding them all. Vescovo's final dive in the Mariana Trench lasted 4 hours. When he returned to the ship, he told reporters he felt like he had been to the edge of the world, that what he saw down there would stay with him forever. He also said something that surprised many people, that as much as he had seen, he was certain there was far more they had missed. The cameras on deep-sea submersibles capture thousands of hours of footage. Most of it is darkness and sediment. Occasionally something moves through the frame, something no one can identify. In 2016, an ROV filming near the Mariana Trench recorded a creature that defied classification. It looked like a translucent sheet, rippling through the water. No visible eyes, no mouth, no skeleton. It moved with deliberate purpose, gliding along the trench floor. The footage was reviewed by marine biologists around the world. No one could say for certain what it was. Some suggested it was a type of actinophore, a comb jelly. Others thought it might be a species of salp, a gelatinous filter feeder. A few researchers argued it was something entirely new. The video has been analysed frame by frame. The creature appears to be several feet long. Its body pulses rhythmically, like breathing. It leaves no trail in the sediment. At one point, it changes direction abruptly, as if responding to something beyond the camera's view. Then, it vanishes into the dark. The ROV never saw it again. This is not an isolated incident. There are dozens of similar recordings, creatures glimpsed once and never again. In 2013, a submersible near the Kermadec Trench filmed something that looked like a jellyfish, except it had too many tentacles, over 40, trailing behind it like hair. The footage lasted 11 seconds before the submersible's lights moved away. Marine biologists who reviewed it could not match it to any known species. In 2018, cameras captured something even stranger. A shadow, moving too fast to be a fish, too large to be an amphipod. It passed through the frame in less than a second. Image analysis suggested it was at least 6 feet long, possibly longer. Some researchers dismissed it as a trick of the light. Others are not so sure. The problem with identifying these creatures is that we have so few reference points. Most deep-sea species have never been brought to the ocean's top layer alive. They die during ascent. Their bodies decompose quickly. What we know about them comes from fragments, partial specimens, blurry photographs. Imagine trying to identify animals on land if you had only ever seen a dozen total species. If every description came from grainy night vision footage, that is what marine biologists face with the deep ocean. Genetic analysis has revealed even more mysteries. Water samples taken from the Hadal Zone contain DNA from organisms that do not match anything in existing databases. This means there are creatures down there we have never seen, not even dead, not even in pieces. Their genetic signatures float in the water, proof of their existence, but we have no idea what they look like, how big they are, how they live. One theory is that the trench acts as a refuge, a place where ancient species survive, species that went extinct everywhere else millions of years ago. The extreme environment protects them. Predators from shallower waters cannot reach them. Competitors cannot survive the pressure. They exist in isolation, frozen in evolutionary time. If this is true, then the Mariana Trench may be home to living fossils, creatures that resemble animals we know only from the fossil record. There is some evidence for this. A type of sea lily, thought to have gone extinct 70 million years ago, was found clinging to rocks in the Java Trench, alive, feeding. Another expedition discovered a species of crustacean that looked almost identical to fossils from the Jurassic period. Almost, but not quite. The differences were small. A slightly different shell structure, variations in the leg joints, enough to suggest evolution had not stopped completely, just slowed. The deep ocean changes creatures in predictable ways. They lose their pigment. Their eyes shrink or disappear. Their metabolisms slow to a crawl. But beyond these basic adaptations, each species is unique, shaped by the specific conditions of its environment. What we are finding in the Mariana Trench challenges assumptions about the limits of life. Every dive brings something unexpected, something that should not exist, and something that makes scientists realize how little they actually know. Scientists divide the ocean into zones based on depth: the sunlit zone, the twilight zone, the midnight zone. Below all of these, at depths greater than 20,000 feet, lies the Hadal zone, named after Hades, the ancient Greek underworld. It is the least studied, least understood layer of the ocean. Less than 0.2% of the ocean floor falls into the Hadal zone. It exists only in trenches, cracks in the Earth's crust where tectonic plates collide and one slides beneath the other. These trenches are scattered around the Pacific Rim, isolated from each other by thousands of miles. Each one is a separate world. Life in the Hadal zone is nothing like life in shallower waters. The pressure is so extreme that gas-filled structures like swim bladders cannot exist. Fish that live here have bodies made mostly of water and gel, compressible materials that do not collapse. They move slowly, conserving energy in an environment where food is scarce. What little nutrition reaches the Hadal zone comes from above, dead organisms sinking through miles of water. By the time they arrive, they have been picked over by scavengers at every depth. What lands on the trench floor is mostly bones and scraps. Yet somehow, life has found a way. Amphipods, small crustaceans, swarm over any organic material that reaches the bottom. They strip it clean in hours. Researchers have used fish carcasses as bait to study these creatures. Cameras placed next to the bait show dozens of amphipods appearing within minutes. Where they come from is unclear. The trench floor appears empty until food arrives. Then, suddenly, there are hundreds. They seem to sense it from a distance, possibly through chemical signals in the water. One of the strangest things about the Hadal zone is how isolated each trench is. An amphipod species living in the Mariana Trench is genetically distinct from amphipods in the Tonga Trench, even though they look almost identical. They have been separated for so long, millions of years, that they have become different species. This pattern repeats across nearly every group of organisms studied. The trenches are like islands, except instead of being isolated by distance above water, they are isolated by depth. A creature adapted to the pressure at the bottom of the Mariana Trench cannot survive in shallower water. The gases dissolved in its body would expand. Its cells would rupture. It is trapped. Some scientists believe the Hadal zone may contain ecosystems we have not even begun to understand. Microbial mats on the trench floor could be processing chemicals in ways that do not happen anywhere else. Symbiotic relationships between species might be so specialized that disrupting one would collapse the entire system. The problem is access. Reaching the Hadal zone requires equipment that only a handful of institutions can afford. Each dive costs hundreds of thousands of dollars. Most expeditions last a few weeks at most. In that time, researchers can sample only a tiny fraction of the trench. Imagine trying to understand a rainforest by examining a single tree. That is the scale of what we are working with. The data we have gathered so far raises more questions than it answers. Why do some trenches have more life than others? What determines which species can survive at full depth and which cannot? How do populations reproduce when individuals are spread across miles of empty trench floor? Some of these questions may never be answered. The Hadal zone is simply too difficult to study, too expensive, too dangerous, Yet every expedition brings back something unexpected. A new species, a strange behavior, a discovery that challenges what we thought we knew. The deepest parts of the ocean are not empty. They are not lifeless. They are alien. And we are only beginning to scratch the surface. The Mariana Trench is famous because it is the deepest. But it is not alone. Around the edges of the Pacific Ocean, there are other cracks in the Earth's crust. Other places where the ocean floor drops away into darkness. Some of these trenches are almost as deep. A few are far less explored. The Tonga Trench, near the island nation of Tonga, reaches a depth of 35,430 feet. Just 400 feet shallower than the Mariana. Until recently, most scientists assumed the two trenches were similar. They are both in the Pacific. Both formed by tectonic subduction. Both lie at the boundary of crustal plates. But expeditions to the Tonga Trench have revealed surprising differences. The water there is warmer, only by a few degrees, but at that depth, a few degrees matter. The sediment has a different composition, more volcanic material, less organic matter. The life found in the Tonga Trench is distinct, species that exist nowhere else. Even compared to the Mariana, farther north, the Kermadec Trench stretches for over 900 miles along the ocean floor near New Zealand. It is slightly shallower than the Mariana, reaching depths of around 32,000 feet. What makes it interesting is the seismic activity. The region experiences frequent earthquakes, some strong enough to trigger underwater landslides. Researchers have recorded avalanches of sediment cascading down the trench walls, burying everything in their path. How life survives in such an unstable environment is a mystery. Amphipods and other scavengers have been found living in areas that were buried under tons of sediment just months earlier. Either they dig themselves out, or they migrate from other parts of the trench. The Kermadec is also one of the few trenches where researchers have detected sound anomalies. Low-frequency vibrations that do not match known sources. Some scientists think they're caused by water moving through cracks in the rock. Others are less certain. In the Western Pacific, the Philippine Trench drops to 34,400 feet. It runs parallel to the Philippine Islands. Unlike the Mariana, which is relatively straight, the Philippine Trench twists and curves, creating pockets and isolated basins. Some of these basins are cut off from the main trench by underwater ridges. Water flows in, but it flows out slowly. Over time, the chemistry changes. Oxygen levels drop. Salinity increases. These isolated pockets may contain ecosystems that are even more specialized than the main trench. Researchers have only visited a handful of them. The Japan Trench, site of the 2011 earthquake that triggered a devastating tsunami, reaches depths of over 27,000 feet. It is shallower than the others, but more studied because of its proximity to Japan. Submersibles and ROVs have made hundreds of dives there. What they found was unsettling. The seafloor in some areas had shifted by over 60 feet during the earthquake. Rock formations that existed before 2011 were gone, replaced by fresh cracks and rifts. Life in the Japan Trench had been disrupted. Fish populations dropped. Scavenger activity decreased. It took years for the ecosystem to recover. The discovery that trenches can change so dramatically in such a short time has implications for every other trench. What we map today may not exist tomorrow. Earthquakes, underwater landslides, volcanic eruptions, all of these reshape the deep ocean in ways we are only beginning to understand. Some scientists have proposed creating a global monitoring network. Sensors placed in trenches around the world, tracking seismic activity, water temperature, chemical composition. The goal would be to understand how these environments change over time, to detect patterns, to predict events before they happen. The technology exists. The funding does not. Until then, Our understanding of the world's trenches remains fragmentary. We know they are different from each other. We know they are dynamic. We know they contain life that exists nowhere else. What we do not know is how much we are missing. Each trench could hold discoveries as significant as anything found in the Mariana. We just have not looked yet. In some places along the trench floor, cracks in the Earth's crust leak superheated water. These vents, called hydrothermal vents, spew fluid that can reach temperatures over 700 degrees Fahrenheit. The water is black with dissolved minerals, iron, sulfur, methane. It billows upward like smoke. Where it meets the cold surrounding water, the minerals precipitate out, forming chimneys of rock that grow taller over time. Some of these structures reach heights of 60 feet or more. They're called black smokers. Around them, life thrives. In an environment that should be completely sterile, there are colonies of creatures packed so densely you can barely see the rock beneath them. Tube worms. Their bodies are white with bright red plumes, extending from the tops. They have no mouths, no digestive systems. Instead, they rely on bacteria living inside their tissues. The bacteria use the chemicals from the vent to produce energy, a process called chemosynthesis. The tube worms absorb the nutrients the bacteria create. This relationship allows them to survive in total darkness, without any input from the sun. Hydrothermal vents near the Mariana Trench are some of the deepest ever discovered. The pressure at that depth makes them different from vents in shallower water. The chemical composition of the fluid changes. Higher concentrations of certain minerals, different temperatures. These variations create unique environments. Species found at deep trench vents do not exist at shallower vents, even when the vents are only a few hundred miles apart. One of the most bizarre creatures found near these vents is the Yeti crab. Its body is covered in hair-like filaments. Researchers initially thought this was for insulation. Later, studies revealed the filaments are coated in bacteria. The crab farms them, waving its claws through the vent fluid to feed the bacteria, then scraping them off and eating them. It is a form of agriculture, practiced by a creature with a brain smaller than a pea. Another common inhabitant is the vent shrimp, blind, translucent. It gathers in swarms around the hottest parts of the vent. Thousands of individuals packed into a space the size of a car. The shrimp feed on bacteria and organic particles in the water. They reproduce rapidly, laying eggs that hatch within days. Their lifespan is short, a few months at most. But in that time, they produce dozens of offspring. Hydrothermal vents do not last forever. The geological activity that creates them can stop suddenly. When the flow of superheated water ceases, the ecosystem collapses. Tube worms die within weeks. Crabs and shrimp disperse, looking for another vent. How they find one is unknown. The vents are scattered across miles of empty ocean floor. There are no landmarks, no obvious trails, yet somehow the creatures locate new vents and colonize them. Researchers believe they follow chemical gradients in the water, detecting minute concentrations of vent fluid and moving toward the source. This ability has allowed vent species to spread across the planet. The same types of organisms have been found at vents in the Atlantic, Pacific, and Indian Oceans, despite being separated by thousands of miles. The vents near the Mariana Trench are particularly interesting because they may be connected to volcanic activity. The trench sits at the boundary of two tectonic plates, one sliding beneath the other. This process generates heat, melting rock, creating magma chambers deep underground. When water seeps into these chambers, it is superheated and expelled through cracks in the seafloor. The cycle can continue for decades, or it can stop tomorrow. Predicting when a vent will go dormant is impossible. Some scientists believe hydrothermal vents may have been where life on Earth began. The chemical-rich environment, the energy from the heat, the protection from harmful radiation. All of these factors make vents ideal for the emergence of simple organisms. If this is true, then studying vents in the deep ocean is like looking back in time, seeing conditions similar to those that existed billions of years ago. The creatures living around these vents today are the descendants of the first life forms, adapted and evolved, but still relying on the same basic chemistry. Every dive to a hydrothermal vent reveals something new, a species no one has seen before, a behavior that does not fit existing models. The deep ocean is full of surprises, and the vents are some of the strangest places in it. People sometimes ask whether there could be something truly massive living at the bottom of the Mariana Trench. A giant squid, a megalodon, some undiscovered leviathan lurking in the dark. The honest answer is that we do not know for certain, but the evidence suggests it is unlikely. Large predators require large amounts of food. In the deep ocean, food is scarce. What little nutrition reaches the trench floor comes from organisms dying at shallower depths and sinking. This creates what scientists call a food-limited environment. There simply is not enough energy to support a large population of big creatures. The largest animals reliably observed at trench depth are fish around 2 feet long, snailfish, eelpouts, species with slow metabolisms and minimal energy needs. They can survive on scraps. A giant predator could not. It would need to consume enormous amounts of food. There is no evidence that much prey exists at full depth. That said, the ocean has surprised us before. The giant squid was considered a myth until a specimen washed ashore in the late 1800s. The megamouth shark, a 15-foot filter feeder, was completely unknown until 1976. New species of large marine animals are discovered every few years, most of them in deep water. So the possibility of something big and undiscovered is not zero. It is just improbable. One theory that occasionally resurfaces is that large creatures might visit the trench temporarily, diving down to feed or reproduce before returning to shallower depths. Sperm whales are known to dive over 6,000 feet to hunt giant squid. Could something similar happen at even greater depths? The problem is physiology. Mammals like whales have lungs. They need to return to the ocean's top layer to breathe. A creature that could dive to 35,000 feet and back would need adaptations we have never seen. Its body would have to withstand pressure changes that would kill any known animal. Its oxygen storage would need to be orders of magnitude greater than even the most specialized deep divers. There is no evidence that such an animal exists. Then there are the sightings. Over the years, sonar equipment has occasionally detected large objects moving near the trench, shapes that do not match known species. Some researchers dismiss these as equipment errors. Sonar can be fooled by underwater terrain, by temperature gradients, by schools of smaller fish clustered together. Others are less certain. At least one sonar reading, taken in the early 2000s, showed something approximately 30 feet long moving along the trench floor. The object was tracked for several minutes before it vanished. No visual confirmation was ever obtained. If there are large undiscovered creatures in the trench, they are either very rare or very good at avoiding detection. Hundreds of hours of video footage have been recorded. Most of it shows small fish, amphipods, jellyfish, nothing approaching the size of a great white shark, let alone something bigger. The laws of biology make it hard for truly massive creatures to exist at extreme depth. Larger bodies require more structural support, bones or cartilage, strong enough to prevent collapse under pressure. Most deep-sea organisms solve this by having minimal skeletons. Soft bodies, gelatinous tissues. A giant predator would need a fundamentally different body plan, none of which we have observed. Still, the trench remains mostly unexplored. We have mapped more of the moon's surface than the Mariana Trench floor. It is possible, however unlikely, that something large exists in areas we have not yet reached. Cameras have only seen a fraction of the trench. ROVs have sampled a tiny percentage of the sediment. There are vast stretches that have never been visited. Until we explore them, We cannot say with absolute certainty what is down there. The deep ocean has humbled scientists before. It will likely do so again. But the smart bet is that the largest creatures in the trench are the ones we already know about. Strange, alien, perfectly adapted to their environment. Just not the monsters of legend. The world's militaries have been interested in the deep ocean for decades. During the Cold War, both the United States and the Soviet Union deployed submarines capable of diving deeper than any civilian vessel. The goal was not scientific, it was strategic. The deep ocean is an ideal place to hide. Submarines running silent at extreme depths are nearly impossible to detect. Sonar struggles to penetrate below a certain threshold. Temperature layers in the water bend sound waves. Underwater terrain creates dead zones where vessels can vanish. The Mariana Trench, in particular, has been of interest to military planners. If a submarine could operate there, it would be undetectable, unreachable. A vessel could sit at the bottom of the trench for weeks, monitoring communications, tracking ships on the ocean's top layer, remaining completely invisible. As far as anyone knows, no military submarine has ever reached full trench depth. The pressure would crush even the strongest hulls. But that has not stopped governments from trying. Classified programs have funded deep-sea research under the guise of scientific exploration. The line between civilian and military interest is blurrier than most people realize. In the 1960s, the United States Navy deployed a series of underwater listening devices called SOSUS, sound surveillance system, arrays of microphones placed on the ocean floor, designed to detect Soviet submarines. Some of these devices were placed near trenches. The recordings they captured included more than just submarine engines. There were sounds no one could identify. Low-frequency vibrations, rhythmic pulses, noises that seemed biological, but too loud to come from any known animal. One recording, made in the Pacific in 1997, was dubbed the Bloop. It was detected by sensors over 3,000 miles apart. The sound was consistent with a massive creature, something far larger than a blue whale. Later analysis suggested it was probably an ice quake, ice cracking and breaking off a glacier. The sound traveling through the water. Probably. Today, interest in the deep ocean has shifted to surveillance and communication. Fiber optic cables that carry internet traffic between continents run along the ocean floor. Some pass near trenches. If a hostile nation wanted to disrupt global communications, cutting these cables would be devastatingly effective. Protecting them requires monitoring. Submarines. ROV sensors placed at strategic points. The trench itself could be used to hide such equipment. A listening device placed at the bottom of the Mariana Trench would be almost impossible to detect. Almost impossible to retrieve. It could operate for years. Powered by thermal or nuclear batteries. Sending data to satellites passing overhead. There is no way to know if this has already been done. The other area of military interest is deep-sea mining. The ocean floor contains vast deposits of rare earth minerals, elements used in electronics, batteries, weapon systems. China currently controls most of the world's supply of these materials. Finding an alternative source is a matter of national security for many countries. The trench and areas around it are rich in these minerals. Extracting them is another question. Mining at extreme depth would require technology that does not exist yet, but governments are funding research, quietly. In 2021, China announced it had deployed a submersible capable of reaching depths over 33,000 feet. The stated purpose was scientific research. The vehicle is also equipped with robotic arms, cameras, sampling tools, everything needed to evaluate mining potential. Other nations are watching closely. The deep ocean is one of the last places on Earth that is not clearly governed by international law. Who owns the Mariana Trench? Who has the right to extract resources from it? These questions are unresolved. The United Nations has attempted to create frameworks for deep sea mining. Progress has been slow. In the meantime, nations are positioning themselves, mapping the ocean floor, testing equipment, building capabilities. The trench is not just a scientific curiosity, it is a strategic asset. And as technology improves, the race to control it is only going to intensify. What happens in the deep ocean may shape geopolitics for the next century. Most people will never know the details, but the decisions being made now will affect everyone. Imagine your body at the bottom of the Mariana Trench. The pressure is over 16,000 pounds per square inch. That is like having 50 jumbo jets stacked on top of you. Every inch of your skin, every organ, every bone, under constant, unrelenting force. What happens is not pretty. The first thing to go would be the air-filled spaces. Your lungs would collapse instantly, completely. The air inside them would compress to a fraction of its original volume. Your sinuses would cave in. Your eardrums would rupture. Any gas in your intestines would be crushed out of existence. You would not feel most of this. At that pressure, unconsciousness would come within seconds. Your brain requires a specific balance of gases to function. When that balance is destroyed, you simply stop. There is no pain, no awareness, just nothing. Your heart would stop shortly after. Not because the muscle fails, but because the pressure distorts the chambers. Blood cannot flow properly. Valves cannot open and close. Within a minute, circulation ceases entirely. The human body is roughly 60% water. Water is incompressible. That works in your favor. Sort of. Your tissues would not be crushed in the way you might imagine. They would not flatten like a pancake. Instead, they would compact. Skin pressed tight against bone. Organs squeezed into smaller spaces. The overall shape would remain recognizable, just smaller, denser. Your skeleton would survive. Bones are strong under compression. They are built to handle forces pushing inward. At trench depth, they would crack in places, especially the skull. But they would not shatter. Fractures would spiderweb across the surface. Tiny fissures spreading through the calcium structure. What would happen over time is more disturbing. Bacteria in your body would continue to function. For a while, they would break down tissues, but the normal process of decomposition requires gas production, bloating, expansion. At the bottom of the trench, this cannot happen. Gas cannot expand. Instead, your body would deflate slowly, collapsing inward as bacteria consume it from the inside. Marine scavengers would do the rest. Amphipods would strip away soft tissue. Within hours, they would reduce a human body to bones and scraps. Fish would pick at what remained. Microbes would colonize the surface. Within a few days, there would be almost nothing left, except the bones, and even those would not last forever. The water at trench depth is slightly acidic. Over years, calcium would leach out of the skeleton. The bones would weaken, crumble, eventually dissolve into the sediment. This is not hypothetical. Researchers have placed animal carcasses at extreme depths to study decomposition. Pig bodies, fish, even a whale carcass once. The results are always the same. Scavengers arrive quickly. They are efficient. Bones last longer, but they do not last indefinitely. The deep ocean erases everything given enough time. There is one exception. If a body were to sink into the sediment quickly, it might be preserved. Buried under layers of silt. Protected from scavengers. The pressure and cold would slow decomposition to almost nothing. In theory, a body could remain mostly intact for thousands of years, mummified by the environment. This has never been confirmed with a human body, but it has happened with other organisms. Ancient fish, crustaceans. Their remains have been found in trench sediment cores, perfectly preserved, as if they died yesterday. The physics of pressure are unforgiving. The human body is not built for the deep ocean. We evolved in air, at normal atmospheric pressure. Taking us to the bottom of the Mariana Trench is like taking a deep-sea fish and throwing it onto land. The environment is incompatible with survival. Yet we are drawn to it. We want to go there, to see it, to understand it. knowing full well that without technology, we would be dead in seconds. There is something both terrifying and fascinating about that. The people who have descended to the bottom of the Mariana Trench all describe the experience as transformative, but they also describe something else. A lingering weight, not physical, psychological. James Cameron said it took him days to feel normal again after his dive. He described it as a kind of sensory hangover. His mind kept returning to the darkness, the isolation, the feeling of being farther from help than any human had ever been. Victor Vescovo has talked about the pressure of responsibility, knowing that if something went wrong, there was no rescue, no backup plan, just you and the machine. He said the stress of that realization hit him hardest after the dive, when he was safe, when he could finally process what he had done. The descent itself is disorienting. It takes hours, sitting in a cramped sphere, watching the light fade, first blue, then purple, then black. The temperature drops. The walls of the submersible creak and groan as the pressure increases. Every sound makes you wonder if something is failing, if the hull is about to give. Pilots say you learn to ignore the noises, that they are normal. The submersible is adjusting, settling. But your brain does not want to believe that. It hears cracking and thinks danger. Once you reach the bottom, there is a brief sense of relief. You made it. You are still alive. Then the reality sets in. You are 7 miles underwater, in a metal sphere the size of a small closet. If anything goes wrong, you have maybe a few hours of air, maybe less. The return journey will take just as long as the descent. There is no quick escape. Some people handle this better than others. Experienced pilots describe a kind of calm that settles in, a focus. You are here to do a job. Film the trench, collect samples, observe. You push the fear aside and get to work. For others, the fear never fully goes away. It sits in the back of your mind, whispering, what if the thrusters fail? What if you cannot ascend? What if the viewport cracks? These are not irrational fears. They are legitimate risks. Every person who has made the dive has signed documents acknowledging that they might not return. After the ascent, when you are back on the ship, there is a strange emptiness. You have been to a place almost no one has seen. You have experienced something most people cannot even imagine. And now you are expected to just go back to normal life. Some divers report trouble sleeping, dreams of being trapped underwater, of sinking, of darkness closing in. Psychologists who work with deep-sea explorers say this is a form of acute stress response, the body and mind processing an experience that pushed them to their limits. It usually fades over time, usually. There is also a sense of disconnection. When you try to describe what you saw, people do not fully understand. They nod. They say it sounds amazing. But they were not there. They did not feel the cold seeping through the walls. They did not see the endless expanse of nothingness stretching in every direction. Victor Vescovo has said he sometimes feels more comfortable talking to other deep-sea explorers than to anyone else. They understand in a way others cannot. James Cameron described the experience as lonely. Even though you are connected to the support ship by radio, even though people are watching the video feed, you are alone down there. Truly alone, in a way that is impossible to replicate anywhere else on Earth. The psychological toll is something researchers are only beginning to study. As more people attempt deep-sea dives, the data will grow. For now, it remains one of the less discussed aspects of exploration. The physical challenges get attention, the engineering, the cost, the danger. But the mental strain is just as real. And for some, it lasts far longer than the dive itself. Companies have spent years studying the ocean floor near the Mariana Trench, not for science, for profit. The sediment down there contains rare earth elements, metals used in smartphones, electric car batteries, wind turbines, elements like neodymium, dysprosium, yttrium. They are difficult to mine on land, controlled by a handful of countries, But the deep ocean has them in abundance, scattered across the seafloor in potato-sized rocks called polymetallic nodules. These nodules form over millions of years, minerals precipitating out of the water, accumulating in layers. They sit on the surface of the sediment, unattached, easy to collect. In theory, the mining process would involve sending machines to the ocean floor, giant vacuums, crawlers with scoops. They would gather the nodules and send them to the ocean's top layer through a pipe. A ship would process the material, separating valuable metals from waste. The waste would be dumped back into the ocean. Environmentalists have warned that this process would be catastrophic. The machines would churn up sediment, creating plumes of particles that could spread for miles, smothering everything in their path. Deep-sea ecosystems are fragile. Species there reproduce slowly, grow slowly, recover slowly. A mining operation could wipe out populations that would take centuries to return, if they return at all. There are also concerns about noise. The equipment used in deep-sea mining is loud. Compressors, pumps, grinding machinery. Sound travels farther underwater than it does in air. Marine life that relies on echolocation could be disoriented, driven from their habitats. Some species might not survive. Despite these concerns, mining companies are moving forward. Test operations have already been conducted in the Pacific. Small scale, experimental, but the technology works. It is only a matter of time before full-scale mining begins. The International Seabed Authority, a United Nations body, is supposed to regulate deep-sea mining. It has been developing rules for years. Progress is slow. Countries disagree on how to balance economic interests with environmental protection. Some nations want strict regulations, others want minimal oversight. In the meantime, companies are staking claims, mapping the ocean floor, identifying the richest deposits. The area around the Mariana Trench is considered particularly valuable. High concentrations of nodules, relatively flat terrain, easy access from international waters. Several companies have already applied for exploration licenses. The economic incentives are enormous. A single square mile of ocean floor can contain millions of dollars worth of metals. Multiply that across thousands of square miles, and the numbers become staggering. Trillions of dollars in untapped resources. For companies and governments, the question is not whether to mine the deep ocean. It is when, and how much. Scientists have tried to push back. Studies have shown that deep-sea mining would damage ecosystems in ways we cannot fully predict. Once the nodules are removed, they are gone. They will not grow back within any human timescale. The creatures that live on and around them would lose their habitats, food sources, shelter. Entire species could go extinct before we even know they exist. Public awareness is low. Most people do not think about where the metals in their devices come from. They do not know that the ocean floor is being targeted. Environmental groups have launched campaigns, trying to raise awareness, trying to pressure governments to halt mining permits. So far, the impact has been limited. The deep ocean is out of sight, out of mind. What happens there feels distant, abstract. But the consequences will not be abstract. They will be real, and they will be permanent. The race to mine the deep ocean is accelerating. Technology is improving. Costs are dropping. Political will is building. Within the next decade, large-scale operations could begin. What we lose in the process may be irreplaceable. The Mariana Trench and the ecosystems around it have existed for millions of years. We are on the verge of altering them forever. For metals, for profit, for progress. Whether that trade is worth it is a question we have not seriously asked. We may not have much time left to decide. Water at the bottom of the Mariana Trench has been sitting there for a very long time. Scientists estimate that some of it has not mixed with the ocean above for over 1,000 years, possibly longer. It is ancient, isolated, trapped by the unique geography of the trench. The way water circulates in the ocean depends on temperature and salinity. Warm water rises, cold, dense water sinks. At the bottom of the trench, the water is as cold and dense as it gets, just above freezing, heavy with dissolved minerals. It settles into the deepest pockets and stays there. Currents at the ocean's top layer do not reach it. The water above moves, the water below remains still. This creates a kind of time capsule. Chemical signatures in the water reflect conditions from centuries ago. Levels of carbon, oxygen, trace elements. By analyzing these, scientists can learn about how the ocean has changed, how much pollution has seeped into even the most remote places, how climate patterns have shifted over time. One of the most surprising discoveries is that the ancient water at the bottom of the trench contains carbon that dates back over 6,000 years. This means organic material from the ocean's top layer took thousands of years to sink and decompose. The deep ocean is not just isolated by distance, it is isolated by time. What happens at the trench floor today reflects processes that started long before recorded history. The water also contains microbes, bacteria and archaea that have been living in isolation for millennia. These organisms have evolved independently from their relatives in shallower water. Their genetic makeup is distinct, in some cases, wildly different. Researchers have found microbial species at the bottom of the trench that do not match anything in existing genetic databases. They are, in a very real sense, alien life that followed a separate evolutionary path. Scientists believe these microbes could hold clues to how life survives in extreme environments, how cells function under crushing pressure, how metabolism works when resources are scarce. Some of the bacteria found in trench water produce enzymes that remain stable at temperatures and pressures that would destroy normal proteins. These enzymes are of intense interest to biotechnology companies. They could be used in industrial processes, pharmaceuticals, materials science. The ancient water also provides a baseline for understanding ocean circulation. Oceanographers use computer models to predict how water moves around the planet, how long it takes for surface water to reach the deep ocean, how pollutants spread. The trench offers a test case, a place where water movement is so slow it can be measured in centuries. By studying it, scientists can refine their models, improve predictions, better understand the global system. There is another implication. If water at the bottom of the trench is truly isolated, it may contain dissolved gases that have been trapped for thousands of years. Methane, carbon dioxide, hydrogen sulfide. These gases are produced by microbial activity and geological processes. In a closed system, they accumulate. Some researchers have speculated that disturbing the trench through mining or other industrial activity could release these gases. If enough methane was suddenly released into the water column, it could affect ocean chemistry, possibly even contribute to atmospheric changes. This is speculative. The volumes involved are probably too small to have a global impact. Probably. The trench remains one of the least understood parts of the ocean. Every sample collected raises new questions. Every measurement reveals complexity. The water there is not just water. It is a record, a living archive of the planet's history, ancient, untouched, holding secrets we are only beginning to uncover. When scientists study the Mariana Trench, they are not just learning about Earth, they are learning about the possibilities for life elsewhere. In our solar system, there are moons with oceans far deeper than anything on our planet. Europa, Enceladus, Titan. These worlds are covered in ice. Beneath that ice, liquid water, miles and miles of it. The conditions in those oceans may be similar to the conditions in the trench. Extreme pressure, total darkness, frigid temperatures. If life can survive at the bottom of the Mariana Trench, it can survive there too. Europa, a moon of Jupiter, is of particular interest. Its ocean is estimated to be over 60 miles deep, more than 10 times deeper than the Mariana Trench. The pressure at the bottom would be unimaginable, yet scientists believe there could be hydrothermal vents down there, cracks in the moon's rocky core, leaking heat and chemicals into the water. just like the vents in Earth's oceans. If that is true, Europa could host ecosystems, microbes, perhaps even larger organisms, living in complete isolation from the sun, thriving on chemistry alone. The lessons we learn from studying life in the trench directly inform how we search for life on other worlds. The organisms we find there show us what is possible. What kinds of adaptations allow life to exist in extreme conditions? What signatures we should look for? Enceladus, a moon of Saturn, has geysers that shoot water into space. Probes have flown through the plumes, analyzing the composition. They detected organic molecules, salts, hydrogen, all the ingredients needed for life. The water comes from an ocean beneath the ice, an ocean under immense pressure. If we want to know whether life exists in that ocean, we need to understand how life works in Earth's deep oceans first. The Mariana Trench is our laboratory. Titan, another moon of Saturn, has lakes and seas on its surface, not water. Liquid methane and ethane. The environment is completely different from Earth, but there are parallels. The pressure at the bottom of Titan seas is comparable to the pressure in Earth's deep ocean. The chemistry is alien, but the physics are the same. Studying how pressure affects organisms in the trench helps scientists predict what could exist on Titan. Even Mars may have had deep oceans billions of years ago. If life ever existed there, it might have survived in the deepest parts, protected from radiation, sheltered from the harsh surface conditions. Understanding how life clings to existence in Earth's trenches gives us a model for how life might have persisted on Mars. The search for extraterrestrial life is one of the biggest questions humanity faces. Are we alone? The answer may be hiding in places we have not thought to look, or in places we have thought to look but cannot reach yet. The Mariana Trench teaches us that life is resilient, that it finds a way, that even in the most inhospitable environments, given the right chemistry and energy, it can survive. This has profound implications. It means the universe is more likely to harbor life than we once thought. It means that oceans on distant worlds are not dead zones. They are possibilities, frontiers. The technology we develop to explore the trench will eventually be used to explore those worlds. Submersibles designed for Earth's oceans could be adapted for Europa's. Sensors built to detect life in the dark waters of the Pacific could search for life beneath the ice of Enceladus. Every mission to the trench is practice for the missions to come. The deep ocean is our analog, our proving ground, the creatures we find there, the ecosystems we study, the chemistry we uncover. All of it prepares us for the moment when we finally reach those distant oceans and ask the question, is there life here too? The Mariana Trench is not just a place on Earth. It is a window into what might exist beyond Earth. And the more we learn, the more we realize how little we know. Not just about the trench, but about the cosmos and our place in it. The Mariana Trench sits at the bottom of the ocean, but in many ways it might as well be on another planet. We have sent 12 people to the moon. Hundreds have traveled to space. Fewer than 5 have been to the deepest part of the trench. We have rovers on Mars sending back images daily. We have probes beyond the solar system. Yet the vast majority of the trench remains unexplored, untouched, unknown. There is a reason for this. Space is hard, but in some ways it is easier than the deep ocean. A spacecraft only has to deal with the vacuum of space. The pressure difference is 14 pounds per square inch, 1 atmosphere, manageable. At the bottom of the trench, the pressure is over 16,000 pounds per square inch, more than 1,000 times greater. The engineering challenges are fundamentally different. In space, you worry about things expanding, seals failing because internal pressure pushes outward. In the deep ocean, you worry about everything collapsing, about pressure crushing inward, about materials buckling under forces they were never designed to handle. Communication is easier in space too. Radio waves travel freely. You can talk to a probe on Mars with a delay of a few minutes. In the deep ocean, radio does not work. water blocks it. You need acoustic signals, sound waves, which travel slowly and are easily distorted. Real time. Communication with a submersible at the bottom of the trench is nearly impossible. There is also the matter of visibility. In space, you can see for light years, stars, planets, galaxies. In the deep ocean, visibility is measured in feet, sometimes inches. The water absorbs light. Even the most powerful lamps on a submersible illuminate only a small bubble of space. Beyond that, darkness. Total and absolute. Yet the trench holds mysteries that rival anything in space. We do not know what lives there. We do not fully understand the geology, the chemistry, the ecosystems. Every dive brings surprises. Things that do not fit our models. Creatures that should not exist. Processes we did not anticipate. The deep ocean is alien in a way that space is not. Space is empty, predictable, governed by laws we understand. The trench is full, chaotic, teeming with life that defies explanation. There is something humbling about that. We like to think of ourselves as explorers, as a species that has conquered the planet. We have climbed the highest mountains, crossed the coldest deserts, reached the poles, but we have not conquered the ocean. Not even close. The trench is proof. It sits just a few hundred miles from inhabited islands, closer to civilization than the surface of Mars. Yet it remains as inaccessible as any place in the universe. The question is whether that will change, whether we will develop the technology to explore it fully, to map every crevice, to catalogue every species, to understand every process, or whether the trench will remain beyond our reach, a place we can visit briefly, but never truly know. For now, it is the latter. The deepest place on Earth is also the most alien. A reminder that exploration is not just about distance, it is about access, about capability, about pushing against the limits of what is possible. The Mariana Trench pushes back harder than almost anywhere else. And maybe that is the point. Maybe some places are meant to remain mysterious, to resist our attempts to uncover them, to remind us that no matter how much we learn, there is always more, always deeper, always further. The trench is not just a geographic location, it is a frontier, one that we have barely begun to explore, and perhaps one that will never be fully explored. Because some frontiers are not meant to be crossed. They are meant to be wondered at, respected, left alone. The deepest place on Earth may be closer than the stars, but in every way that matters, it is just as far away.